We have Dallas Montgomery and Mike Kronander with Burgess Niple. And so if you would welcome them, please.
Thank you all for coming this morning, and welcome to our presentation on diagnosing and rehabilitation of deficiencies in 4 Ohio post-tension bridges. As we were introduced, I'm Mike Kronander, bridge engineer at Burgess and Niple. Dallas Montgomery will also be participating in this presentation with me. He is our post-tension cable stay expert at Burgess and Niple. So overall teamwork experience, myself personally, I've been dealing with these kind of structures for about 4 or 5 years now at Burgess and Niple. Dallas here has the wealth of experience with over about 15 years with all these different structures, and the testing is what we're going to kind of show you, inspection, construction. He's worked with a team of experts on this for years now, and on these particular bridges we'll be talking about today in these case studies, our team consisted of B&N, Structural Technologies, and SEVA Corrosion Services. So with the scope of services, in the first phase, basically there was 11 bridges total that we looked at. And what we wanted to do with those 11 bridges is do kind of like a assessment based off of inspections. So we did visual inspections, kind of what you would do with a normal routine or in-depth inspection on a bridge, to kind of determine which bridges we were going to go with further into those other phases and do testing, NDT, and invasive testing. And that led to phase 2. So after we picked those 4 bridges for that testing, then we went on and did generation of construction plans for rehabilitation. And then after that, we also provided expertise on the construction process during the repairs of each of those bridges. Just this slide just kind of shows you the 4 different structures. I will be talking about bridges A and B, which are post-tension box girders, 3 spans and 5 spans. And then there's also a couple of structures that had post-tension pier caps that Dallas will be talking about more. These bridges are all located right in downtown Cincinnati. Cincinnati Red Stadium is right there in ODOT's Ohio Department of Transportation's District 8. So I'd also like to thank ODOT for this project and this opportunity to work on this. Brandy Collette, the district engineer, he was a big help in the whole process of this, developing this project and working with us. He was great as well. So here, this will just show you just kind of a breakdown of post-tension tendon profile on one of the bridges. This is the 3-span bridge, Bridge A. So what I want to highlight here is if you look at where the pier would be, where that high point of the tendon profile is, when I get into more of the testing phase of it and explaining it, that is, we try to get as close as we can to where that high point of that elevation of that tendon profile is. Also, we do the same thing at the anchor. The anchor isn't as high as where it is over the pier, but we try to get as close as we can. You can see the highest point is actually not even accessible because it's right below the deck, and it's right where that pier diaphragm would be. Now, why we do this is when they're grouting, they start from the low point, and then they push it up. So where your voids and your problems are going to develop is right at that highest point where those air pockets can form. And it's right below the deck there where the cracks can occur and cause like moisture and infiltration of different contaminants into that duct area, causing your issues if you do have voids in the grout. The other thing is with the pumping process is ventilation. So I don't have the vents labeled on here, but usually nowadays they want to try to vent it properly and put 1 on each side at least, and 2 vents. In the past, they've only used 1 vent, and the problem with that is if you pump it over that hill there, then you just have that 1 vent, and you're not sure if you're completely filling that air pocket up there, and you just don't know unless you actually check it. And in the past, they haven't checked it, so that's why we tried to focus our testing in those particular areas. So as I was speaking before, so getting into the testing process in these bridges, we're on the inside of them now. This is one of the box girder bridges, and on the picture on the right, or on the left, sorry, you can see yellow lines. So we use a handheld GPR unit to lay out where the rebar is so we don't cut into that reinforcing steel. And then that red line is going to highlight where that crimped steel 4-inch diameter duct is going to be. And we try to pinpoint where that center line is of that duct. And then the picture on the right, after we find out where the duct is, we're going to try to avoid that rebar and then drill all the way down into that duct into the web wall. After we locate the duct and get to it, then we'll use a hammer and a flathead screwdriver there to kind of pry open the duct. And then after we pry it open, then we'll use the borescope insert there to just do a full investigation of what the existing conditions are around that duct and the cables and the grout. So the picture on the left is a duct that's full of grout, so you can always tell when they're hitting on it too. So when they start hitting on it, obviously if it's full, you don't get that little thump and fall into it, and then you can see like they do this a little bit if there is a void in there. And then if there is a void, that allows us to do a little bit more in-depth analysis with the borescope and kind of squeeze it in there more to see it exactly what's going on, especially with if the cables are exposed or not. With this slide, this just kind of shows you the initial development stages of a little bit of corrosion, especially on these exposed cable strands here. So the issue with this is like, you see this and it's just light corrosion. So if you're a bridge inspector going out and you see corrosion, oh, that's condition state 2, obviously. But with the problem is you have corrosion on mild reinforcement, and these are post-tension strands. So because they see all that tension, yes, this is not an issue yet, but if that corrosion keeps advancing and you start getting pitting and section loss, these strands are much more induced and prone to failure, much more than a mild reinforcement would be. And this is one of the reasons why we're kind of showing you this, of like why we do this invasive testing or non-destructive testing, to try to catch these issues before they get out of control or out of hand, and the repairs or remediation would be very difficult to do. Other than the borescope testing side of it, we also perform corrosion rate testing, where in this particular area, what we do is they actually chip out a big box of concrete all the way down to the duct, and then they use an angle grinder to cut open the steel duct there. So with the corrosion rate on the left there, that exposes the entire tendon bundle, and then we can hook up all the equipment to perform the corrosion rate testing. And then on the other side, if there's grout there, we can chip off a little bit of grout and collect that for sampling. And we usually will take that back for lab analysis. We'll test for chlorides, sulfates, do petrographic analysis, carbonation, pH levels, just a bunch of different things when we take it back to the lab. And we'll do this at a few different areas of the bridges, usually at least 2 or 3, I'd say. This just shows you more photos that we found with the borescope. The one photo on the left just kind of shows a little bit of what grout is left on those exposed cables there, or strands. And then on the right, you don't see the corrosion on the strands this time, but you happen to see signs of moisture and the corrosion on the inside of that steel duct. So we discovered this, and we deemed it the Niagara hole, as we like to call it. But so when they drilled into the duct on this one, this was Bridge B, the 5-span bridge. This water, I don't have the entire video, but it was pouring out for 5 or 10 minutes or so, and probably was around like 5 to 10 gallons of water, I'd say. It just kind of shows you never know what you're going to find. But the water looked mostly clean when it was coming out. But yeah, it just kept coming and coming and coming, and there's a lot of water in there. So summarizing the overall conditions, what we found in Bridge A in particular now. So there were a lot of cracks in the deck and the box girder themselves. So why that happened is we discovered that after looking through the plans, that they used a lower strength concrete, and that's why a lot of those cracks developed initially post-construction. The chloride contents and sulfate contents were kind of at normal thresholds. Nothing too alarming there when the grout went back for analysis. There's a high pH also found in the grout, which is good when you get that high pH and it's not seeing carbonation. That produces a passive film on the steel strands themselves and kind of adds another extra layer of protection on there if there is grout around it. So we did kind of like full testing on all the high points on this bridge, and we found that over 50% of them had voids. And these voids, we determined, like, basically they have to be at least 1/4 of an inch so we can kind of fit the borescope in there. And then we found voids, as you saw in some of those pictures, that at least half the duct was exposing those steel strands in there. There is also signs of light corrosion on the strands and the moisture around the duct itself in the interior. And as I kind of explained before with those, when you get the cracking in the deck, and that highest point of that tendon profile is directly below the deck, obviously you're going to get issues in there if water and other contaminants are getting through those cracks in the top of the deck. The good thing about this bridge, though, is only 18 years old, and like I said, we found it where we didn't find any worse corrosion on the strands themselves than what I showed you in those pictures. So by finding those right away, then that gives plenty of time, and you can develop a good plan of action after we commence our testing for this bridge. Also, the grout that we found was of good quality. The contaminant levels were normal, and same thing with the pH, as I mentioned. Similar things we found for Bridge B. The video, that was this 5-span bridge that had the Niagara hole. And then not as many voids we found with this one, only 20%, but we also found some voids that also there was basically no grout inside of the duct there, and the entire diameter or full size of the duct of 4 inches was exposing those strands. So after finding our conditions and doing our testing, we decided to come up with some recommendations to help kind of prevent any further corrosion of the PTS in the bridge and kind of mitigate the issues that we found. So what will help with the deck is, if there is cracking, is to add some type of sealant or flood coat on that to prevent any more water or contaminants from getting through there to reach those ducts. And then obviously that's your outer protection layer, the concrete surrounding the encased duct. And then you have the duct itself, which the crimped steel. The problem with the crimped steel ones nowadays is that they're not exactly watertight or airtight. So it's really key to make sure that everything around it, especially your concrete surrounding the duct, and then inside of it with the grout as well, it's fully grouted, and the grout is of good quality, protecting those strands. So with the voids that we found, we're going to do remedial grouting, and that we usually use current ASBE and PTI specifications for that. Since we performed basically all the high point borescope testing, if you perform all the remedial grouting that you need to and find all the voids, then no further borescope testing would be needed. We want to try to do corrosion rate analysis and grout analysis every 10 years or so to check for carbonation reaction in that grout again. When we did the initial inspection and we were inside the boxes, there was lots of diagonal shear cracking in the webs, so we usually marked all those out when we were in there, so you just want to continue to monitor those. Most of them were not significant. They're very minor in width and size, but you want to keep an eye on those. And then it's always good to also perform a baseline survey to check for any sags in the overall profile of the box girder or any deflections that may be an anomaly. With that, I will turn it over to Dallas, and he will continue on the presentation and starting with this Pure Cap 2 for Bridge C.
Thank you, Mike. Bridge C consisted of Pier 2, Bridge D consisted of Piers 3 and Piers 4. We have a similar situation. The tendons run longitudinally along the length of the pier caps. They run from, in this case, from the south to the north. Again, you like to try to test at the high points because that's where if you want to have any voids, that's where the water hydrates up to if you got too much water in the grout, and then it forms a void once the water rehydrates back into the grout. So this is Pier 2, but one thing I want to point out in that bottom right picture, that is where the anchors are buried into the pier caps several inches, and that's called a block out. And the block out on this structure was intended to be put back with a non-shrink grout so there would not be shrinkage cracks between the concrete of the pier in the grout of the blockout material. That did not happen. They used regular concrete, so essentially there was shrinkage cracks around all of the blockouts at all three piers, or six ends total, because each pier, of course, has an end. This is just a rough diagram of the Pier 2 in elevation view. This is a picture looking east on the west side. The left side is the north side, which is a little bit of a higher point, but not the highest point. And normally we would check the south end, which would be where the high points are, in the most likely event of where the voids would be. But for Pier 2, and I'll get to that in a minute, this is what you're looking for when the grouting operation is complete. During the grouting operation, then shortly thereafter, if you have water separate, bleed water separate from the grout, the water is, of course, lighter than the cement itself, so it's going to go to the highest point, and it can form a void. Once that grout sets up and hydrates, the water then rehydrates back in, and you're left with a void right where that red area is. And in Pier 2, the grout port that we show at the top, it was completely empty, and we'll show you a picture of that in a minute. So due to the fact that we had a lot of cracks and efflorescence at the north end of Pier 2, we decided to start testing there instead of at the very high end, which would have been the south end. And when we opened up the first one, that's the picture top right and bottom right. Once we chipped away everything, cleaned off, exposed the anchor plate, strand tails, and the wedges, everything looked really good. And although we knew we could come back to here, we thought, let's go to the south end where the two high points are and see what happens. And this is what we saw. These pictures do not do it enough justice, but essentially we have exposed the anchor plate, strand tails, and the wedges. And in the picture to the left, you see where that is the grout vent. It's completely empty, and we'll take a little closer look at that here in just a minute. But all of the dark areas on all three of these is moisture that had flowed in between the regular concrete of the blockout and the concrete of the pier cap. And of course it evaporated within a few hours, but all of it was pretty wet on the inside. And that was accessing right into the anchorage area, which is the danger zone that you do not want air and water getting into. So we took the grout vent and we ran a borescope down into it, and that bottom left photo shows you as we're going down into it, it's heavily corroded. So you've got water and air entering into this area. The picture to the far right, you can't really tell it. It's a two-dimensional view, so you really can't tell it. But at the bottom of it is a 1/4 inch void. So it didn't have a very big void, but we don't know how much water has entered into here. More than likely, given the state of the grout vent, there probably was just beginning to be a lot of water flowing into this particular area, but probably not a bad situation at this point in time. So the summary conditions of testing at Bridge C is we tested 4 locations. 2 of the locations had water infiltration and corrosion to deficiencies of the anchor wedges and strand tails. That accounts for about a 50% potential deficiency rate. You've got 8 tendons in Pier 2. That gives you 16 anchors. If you extrapolate that out, you potentially have 16 locations that could be have deficiencies. Now, at this point, at stage of the testing, we could have gone ahead and essentially said we needed to chip out all of the concrete in the blockouts at all 6 locations and check everything. But that's a very extensive operation to do, and it's really a operation that's much better to do during the rehabilitation than it is during the testing, because chipping them out and putting them back properly, as you'll see in a minute, is a pretty extensive operation. So our suggestion was to the client is don't spend your money doing more testing here. Save your money for the rehabilitation, which I think they greatly appreciated because everybody's got never enough money for anything. So they were pretty happy with that suggestion because at all 6 locations, you've got the shrinkage cracks and you're going to have eventually water one way or the other flowing down into those anchor areas. So the recommendations for pier caps 2, 3, and 4 at bridge C and D, this was our initial recommendations, is that the heads, the total blockout concrete should be removed, the anchor heads and so forth should be totally cleaned and inspected. Any voids in the anchor trumpets and the upper portion of the anchorage should be completely filled. All anchor heads should be attached an ASBE and PTI standard plastic cap. You would then fill that with a thexotropic grout to completely seal it. Then you would take the outside and use a non-shrink grout to pour that block out back in, and then you would finish off with covering with the urethane coating. Now that would be our normal recommendation. But we talking with the client and going back with several different options, we decided that we would go a different route, and I'll cover that in just a minute. Our rehabilitation plans for bridges A and B, box girders, essentially is we went by the PTI and ASBE recommendations. We used a 0 thexotropic grout compatible with existing material, which our laboratory analysis said was okay to use. And we did remedial grouting of plans for the remedial grouting of all the voids. And the prime contractor that performed this work on all 4 of the bridges was Fresnay USA. And the rehabilitation plan, this is just for piers 2, 3, and 4. We essentially called for the list of a normal repair operation for that. But the problem we had is we could not check into the sides of the pier caps because the tendons were so deep, we would have done the patient more harm than good by doing that. So since we couldn't test in there, the decision was made that instead of filling the new caps with grout, we would go ahead and use Vector's corrosion post-tech system, which essentially is a very low viscosity fluid that is pumped under low pressure from one end of the pier cap, and it's pumped all the way through, goes in, impregnates the strands and the concrete around it, and then comes out the other end. Usually takes about 24 hours for that to happen. In laboratory and research projects, we've found that it does prevent corrosion of the steel. It's still a relatively new product, so only time will tell, but it holds a lot of promise. So the client felt very comfortable saying, let's go that route. So the actual rehabilitation is started with the bridges A and B, the box girders. The picture to the left is, the main thing with the grout is you want quality control, quality, QA/QC, all the way through the whole process. So the test to the left is a mud balance. Essentially, it is calculating the density. From the density, you can decide how much water is in there, what the water-cement ratio is. You do not want the water-cement ratio to be over 0.45. The picture to the right is a flow cone. You want the grout to be fluid enough to reach into all the corners in nooks and crannies of the cavity, but you do not want it to be so fluid that it's got too much water with it. So the flow cone is a test that we do as well. So these 2 tests in tandem are performed several times during the course of a day. This picture, the picture to the left, is just actually the pumping equipment. When it comes to remedial grouting, you have 3 types of grouting possible. You have vacuum grouting, pressure vacuum grouting, and pressure grouting. We all ultimately couldn't pull a vacuum, so we used pressure grouting at all locations. So this essentially is setting up the pier caps to be repaired. We did epoxy grouting at Pier 2 to seal those big cracks. This is the vector impregnation setup that we used. After the impregnation was done, we set up forms at all the blockouts, and the picture to the right is a chute where you poured it in there. This is actually pouring the grout into the blockout areas. Once it's done, picture to the left shows you what it looks like. It's completely covered the blockout. So that's ground nice and smooth, and the picture to the right is the final product, which is urethane coated several times. Now this bridge is good for the life, its service life, 50, 75 years. The blockouts would be in good shape. So the main thing is, most of our testing happens on 20-year-old bridges or older. When you get to your newer bridges, although you still can have issues, a lot of states have gone to testing at the time of construction 100% of the potential void locations. So with that in mind, is there any questions?
Did the original construction use fixed-topic grouts?
No, it did not really exist at that time. This bridge was 18 years, it's 22 years old now, so it was in the early 2000s, so you didn't have it.
During your analysis phase of that grouting depth, do you get an estimate of the volume of void that you might be looking at?
Yes, we do, and it's usually not even close. It tends to be higher than what we calculate, because that's very difficult to calculate. Now, grout's not cheap, but the real cost in it is the labor, getting it there. So if you can get pretty close, then the contractor, he has the plans, he can do his own calculations too.
What are the approximate dates that you did the inspection and then the rehabilitation?
We did the inspection back in 2008, testing and inspection 2018, and then we did the testing later on in that year. Then the next year came around and we did the rehabilitation plans during the winter, and then in 2019 did the actual rehabilitation. Thank you very much.
Do you guys have a booth? Do you have a booth there? Applause for Dallas and Mike.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.